Nuclear decay equations can look intimidating at first glance, but the physics behind them is built on basic addition and subtraction. By the end of this video, you will be able to balance these reactions, identify unknown elements, and understand the concept of a radioactive half-life. To begin, you need to know how to read a standard element symbol. The letter is the element itself. The blue number on the top left is the mass number, represented by the letter A. The red number on the bottom left is the atomic number, represented by the letter Z. This top and bottom layout is the foundation for every calculation we are going to perform. Radioactivity is a spontaneous transformation. A parent nucleus splits apart, resulting in a daughter nucleus and the emission of a radioactive particle. To find the daughter nucleus, we apply the law of conservation. The reaction arrow serves as an equal sign. The sum of the mass numbers on the left must equal the right. The same is true for the bottom row's atomic numbers. Because these numbers are conserved, we can solve for any missing value as long as we know the specific numbers for the particles being emitted. There are 4 common particles. Alpha has mass 4, atomic number 2, and is stopped by paper. Beta minus has 0 and -1, stopped by aluminum. Beta plus has 0 and +1. Gamma has 0 and 0, stopped by thick lead. Memorizing these 4 sets of numbers is necessary to solve any decay equation you encounter on an exam. Let's apply these values to a real-world example, the alpha decay of bismuth-212. With bismuth-212 on the left, we place unknown X and alpha on the right. Substituting alpha's values, 4 top, 2 bottom, we solve the top row. 212 equals A plus 4, giving 208. The bottom row, 83 equals Z plus 2, giving 81. Every element has a unique atomic number. Because our Z value is 81, we can confirm the daughter nucleus is thallium. Next, we will look at bismuth-210 undergoing beta minus decay, which requires careful attention to the bottom row math. We set up bismuth on the left, unknown X, and beta minus on the right. Beta minus carries a -1 atomic number. Be precise, 83 equals Z plus -1. Moving -1 across the equal sign changes it to +1, equaling 84. With an atomic number of 84, we can identify this element as polonium. Beyond identifying the elements created, we also measure the time it takes for these transformations to occur. This is the half-life. The half-life is the duration required for exactly 1/2 of the atoms in a radioactive sample to decay. Imagine we start with a sample mass labeled M0. We use this clock to track the time. When the clock reaches interval T, 1 half-life has passed. The initial mass is reduced by half, leaving M0 over 2. It is important to remember that half-life is always a measurement of time, not a measurement of the mass itself. You now have a reliable process for balancing nuclear equations, identifying the particle values, applying the law of conservation, and accurately handling negative integers in the bottom row. Let's see if you can apply these steps to a final practice problem. Uranium-238 is undergoing alpha decay. You need to determine the mass number and atomic number for the resulting daughter nucleus. Run the math for both the top and bottom rows, and put your final numbers and the name of the element in the comments.